Welcome to 120 lectures. Math 120 is a continuation of 119. Basically, we will cover the basic calculus concepts in the case of multivariable functions. That means we will be considering limits, derivatives, and integrals of functions of several variables. But we will be starting with sequences and series, which are quite important in mathematics. And somehow they don't seem to fit into multivariable calculus. You can consider this as a continuation of the first part. So let me start with sequences. We are familiar with the concept of sequences. For example, consider what you are going to do the next day. Okay. For example, you will wake up, you will wash yourself, and then you will have breakfast. And after breakfast, you will perhaps go to school, and on your way back, you will visit a market, and so on. Note that in this sequence of things to do, one very important thing is that you must do these things in a certain order. That's to say, you don't first have breakfast and then wake up. So the order is the basic concept behind a sequence. Okay. It is not the order of the things you do, but rather when you do them, or basically the locations there. Well, mathematically, we show these in this format. The important thing here is not the values A1, A2, A3, but the positions. So, a sequence can be considered as values assigned to positions. So, in the first position, that is here, okay, you have a value A1. This can be anything, not necessarily a number, even though we will be considering number sequences. Well, let me give you two examples. Okay. Okay, as a first example, consider a sequence of this form. Okay. This is the sequence of natural numbers. Well, there might be a confusion with a set. Okay. We use the same notation, but here we are observing the order. So it is extremely important. Or I could consider the same set in this form. Note that the terms are exactly the same. So as a set, they seem to be the same thing, but as sequences, they are different, because the order has changed. So Okay, these are both natural numbers represented in a certain order, but these are different sequences. Since order is changed. Okay. Well, of course, a sequence need not have numbers as the values. For example, we could have considered a sequence of the form 1, okay, a diamond, 3, again a diamond, 4, again a diamond, and so on. Okay. Then when we look at these sequences, okay, we observe that we can determine, okay, what happens at a certain position. So a sequence assigns a value to each location, or if you want, position. Okay. So in example 1, okay, our A1 will be 1. This means that to the first position, okay, the value is 1. Okay. Similarly, say at the 10th position, we have 10. Or in the third example, okay, our first term, that is 1, this is the value assigned to the first position, but then at the second position, we have a diamond, and so on. Now you can determine what happens at A, for example, 12. In the 12th position, in the third example, okay, clearly you will have a diamond. All of these are sequences, okay? But they are different sequences. Now when we look at the statement that it assigns a value to each location, which means natural numbers, of course, we sense a function definition. Well, a function takes an element from its domain, assigns a value from the range. Well, a sequence takes a position determined by first position, second position, or 10th position, or 12th position, so a natural number, and gives us some value. Could be a number or a non-number. So this tells us that we can define a sequence as a function. So, okay, a formal definition a sequence is a function with domain natural numbers. So for every natural number, it gives us a value. Well, the values are not that important. So let me emphasize here that we will be considering sequences with values in real numbers, basically. Okay. So we will be considering functions defined on n and into R. Hence, any function defined from n into R is a sequence. Okay. Now, having noted this definition, that is, considering sequences as functions, okay, we can then consider the examples. In our previous examples then, in one, recall that it assigns the same n at the nth place, so the sequence is determined by this function. Okay, in the third example, g of n, so let us look at the third example. It's not a number sequence, but anyway, at odd integers, you have the same integer itself. And at even integers, you have a diamond. So it's a piecewisely defined function. Thus, it happens that it is equal to n itself if n is an odd number, and it is a diamond if n is an even number. So this is a piecewisely defined function. It's the sequence in 3. Well, we don't usually use the notation f of n for a sequence, but rather the notation I wrote at the very beginning, and we say a sub n. That's a usual notation for a sequence. So let me say a few things about the notation of showing a sequence. So we show a sequence by one of the following ways. The first one, of course, is to write down the values. Or we say that it is a n from 1 to infinity. Or you can put a function, use f, but these are the basic ways of showing a sequence. Okay. Well, being a function, then we can ask the question, which properties of functions can a sequence have? So, let us consider now here the properties. Of sequences. okay, of course, regarded as a function. So, what properties does a function have? We will assume here that our sequence has real values. Okay. Well, what can these be? First of all, okay, we have the notion of a bounded function for a real valued function. So, let us recall that if f is a function from R into R, then f is bounded. I will simply write in abbreviated form BDD. If there is a constant such that the absolute value of f of x is smaller than or equal to m for every x. Okay, this was our definition. In the sequence version, okay, this becomes f from n into r, that's a sequence, okay, and I will show f of n as an, is bounded, okay, if there is an m such that an is less than or equal to m for every n, because the domain is natural numbers. Well, this definition makes perfect sense. So, this is our definition. A sequence is bounded if there is an m, so that all values of the sequence are bounded by this m. Okay. A second property, that's about monotonicity. So, let us again recall that a function R into R is increasing if you take the variable and compare it, okay, with a larger variable and consider the values should increase. So if x increases, f of x should increase. This is characterized by saying, let us recall that, for any x1 and x2, so that x1 is smaller, okay, one has f of x1 is less than or equal to f of x2. Okay. And recall, we said strictly increasing if we had strict inequality here. Now, for sequences, this becomes that is, if f is a function from n into R, again, I will write f of n is an, because it's a sequence. Okay. This means that for every n less than m, okay, f of n must be less than or equal to f of m, copying the same thing. Now, this property, okay, again, makes sense. We can define an increasing function this way, okay. So I should say here is increasing, okay, if this is true. So then, but this property is the same as saying that for every n, an is less than or equal to an plus 1. Okay. Why is that so? Well, we know here that f of n, that is an, is less than or equal to am if n is less than m. Well, put m, n plus 1, you get this. Conversely, if this is true for every n, it means that an plus 1 is less than or equal to an plus 2. And if you continue that way, you reach am. So this definition is equivalent to saying that this is true. And so this will be our definition. So, okay, we say a sequence an is increasing if for every n this is true. Okay. Now, we can define a decreasing sequence in a similar way. That is to say, okay, we say similarly, a sequence an is decreasing if for every n, an is greater than or equal to an plus 1. That is, if we increase n, the value becomes smaller. So these are the basic definitions. And let me just here note that if the inequalities are strict, then we use the terms strictly increasing, respectively, strictly decreasing. So, strictly increasing, okay, or strictly decreasing if an is less than an plus 1, respectively, an is strictly greater than an plus 1. Okay. We will be using these terms as well. Okay. Well, let us see some examples. Okay, let an be n over n plus 1 for every n. Now, this defines a sequence. Certainly, it's a nice function from n. Well, if we look at the difference between an and an plus 1, okay, we see that this is n over n plus 1 minus, okay, in an plus 1, we replace n with n plus 1. So it becomes n plus 1 over n plus 1 plus 1. Okay. Now this happens to be, okay, n squared plus 2n minus n squared minus 2n minus 1 over n plus 1 n plus 2. Okay. Of course, this says that all these cancel out, so this is negative all the time for every n. Okay, because it's negative all the time, it means that an is strictly less than an plus 1 for every n. So the sequence an, okay, increases strictly. Okay. Furthermore, the absolute value of an, which is n over n plus 1, is always less than or equal to 1. So AN is bounded as well. So it's a strictly increasing bounded sequence. Okay. As a second example, let us consider AN be 1 over n for every. Then, of course, okay, AN, which is 1 over n, is certainly greater than 1 over n plus 1 for every n, which is AN plus 1. Actually, it's strictly greater than. Well, this is true for every n. So the sequence, okay, decreases strictly. As in the previous case, certainly it is bounded. It's bounded by 1. Okay, so these are some examples of strictly increasing and decreasing sequences. Now, as a third example, let us consider AN as minus 1 to the n over n for every n. Now, let us compare A1 with A2. Okay, A1 would be minus 1 over 1. A2 would be 1 over 2. So clearly, we have this inequality. So if we increase 1 to 2, we get a larger number. Now let us try A2, which is 1/2, and compare it with A3, which is minus 1 over 3. Okay. Clearly, we have the opposite inequality here. Now, this tells us that for every n, okay, increasing property is not satisfied. And this tells us that decreasing property is not satisfied for every n. So, these show that the sequence minus 1 to the n over n is neither increasing nor decreasing. So it happens that a sequence need not be monotone, as in the case of functions of real values. Of course, a natural question would be, what other properties can a sequence have? Because we are considering the calculus point of view, certainly the first thing that comes to our minds is, what's the limit of a sequence? When is a sequence continuous? When is it differentiable? Well, let us consider these properties one by one. before we venture into this problem, let us recall what we mean by the limit. Recall that if f is a function from R into R, okay, not a sequence, then, okay, limit x approaching x0, f of x is L, means exactly the following. For all epsilon, we could find a delta such that if x minus x0 is less than delta, then f of x minus L is less than epsilon. Okay, this, of course, says that if x is near x0, then f of x is near L, which is the basic idea behind the limit. Now, for sequences, what does this mean? Okay. So, let, say, Gn be An, and repeat the same argument. So this would mean that limit, okay, variable is an integer, and integers are in the domain. So this limit, okay, which of course is the limit n going to n0, An, is L, should mean the following. Okay. For all epsilon, there is a delta such that if n minus n0 is less than delta, then An minus L would be less than epsilon. Now let us look at this statement more carefully. What does it say? Well, in the original definition, clearly if this is true for every delta, it will remain true if delta is smaller. Okay? Because the nearer x is to x0, okay, the better this approximation here. That's the spirit of the limit. Now, when we look at this last statement for sequences, okay, let us consider the assumption that the difference between n and n0 is between 0 and delta. Now, if delta is strictly less than 1, it has to be a positive number anyway. If it's strictly less than 1, then this inequality, that is the condition never holds. Okay, because the difference between two distinct integers is at least 1. It cannot be less than 1/2. And if they are the same integers, we don't allow it. They have to be different. So this is not true, okay, for any n and for any n0. Okay. Well, this means, in fact, that is, okay, an integer cannot come closer to another integer. okay, then, okay, 1. That's to say, the distance between two integers, okay, is either 1 or larger. You cannot make the distance between them smaller. Okay, so we conclude that this definition is quite inappropriate and it means nothing. It's meaningless for a sequence. So limit n going to n0, an is meaningless. So we conclude at a point we don't have the concept of a limit for a sequence. So, okay, limit. If we don't have a limit, we don't have continuity. If we don't have continuity, we don't have derivative. Our sequence at a point, okay, is meaningless. So we don't have any of these concepts for a sequence. Yeah. But we have let out one possibility. That is, if x does not go to x0, but if x goes to infinity. Well, in the sequence version, if n goes to infinity, well, this is not an impossibility. N can go to infinity. Actually, it does. Okay. So this is quite a meaningful definition for a sequence. We did not consider this possibility. Let us recall what this means in the case of a real variable function. Okay. For every epsilon, you can find a number such that if x is near infinity, we measure it by saying that if x is bigger than m, then f of x is near L. This was the definition of f of x going to L if x goes to infinity. Okay. Now for sequences, okay, this means that, okay, limit n going to infinity, an is L. Okay, this means for all epsilon, you can find an m, okay, such that if n is greater than this m, then an minus L is less than epsilon. Now, since an arbitrary real number m is not in the domain of a function, well, necessarily it shouldn't be, but let us replace this m with an integer. The same argument, still valid. So we can make a little change here, okay? Because this m is supposed to be a number near infinity, that is a very large number, we can take it as a very large integer, because it's the domain anyway. So let us make a little modification. So modify to a 0. So this means that the limit n going to infinity of an is L, means exactly that for all epsilon, there is an n0 for every n greater than n0, I mean less than or equal to whatever, one has an minus L is less than epsilon. Okay. So this will be our definition. So we can talk about n going to infinity for a sequence, and it means that after some n0, the distance between the values of this sequence and the limit value will be as small as we want it to be. Okay.